Okay, so picture this. It's 1907, and Albert Einstein is totally stuck. I mean, he just turned physics on its head with special relativity, but there was a huge gaping hole in it. It had nothing to say about gravity. So figuring out how to fit gravity into this new reality he'd uncovered, well, that puzzle led him to what he later called the happiest thought of his entire life. And it all kicked off with a really simple, almost childlike question. Let's get into it.
So how do you get rid of gravity? I mean, that sounds impossible, right? It's literally what's holding you in your chair right now. It keeps the Earth circling the sun. It feels totally inescapable. But what if I told you there was a way to just switch it off, even for just a little while?
And this is it. This is the moment it all clicked for Einstein. He imagined a man falling from a roof. Now, during that fall, for those terrifying few seconds, that man wouldn't feel his own weight. If he took keys out of his pocket, they wouldn't fall down. They'd just float right there next to him. In his own little bubble of existence, gravity would have just vanished.
So yeah, the simple kind of shocking answer is you get rid of gravity by falling. And you've seen this. Astronauts floating around on the International Space Station, that station is in a constant state of freefall around the Earth. Or, those people on the Vomit Comet, that airplane that makes big stomach-churning arcs in the sky. For a few moments, they are simply falling, and for them, poof, gravity's gone.
This idea, this happiest thought, wasn't just some clever riddle. It became the absolute cornerstone, the bridge he needed to get from special relativity to his masterpiece, general relativity. It's all about this idea of a local escape from gravity. And of course, Einstein gave this a proper physics name, a local inertial frame. Just think of it like your own personal temporary bubble of space-time when you're in freefall. Inside that bubble, you're weightless, and all the rules of his 1905 theory, special relativity, they all work perfectly. The key word here, though, is local. This magic bubble is small, and it doesn't last forever.
And this is where it all leads. It's a conclusion that completely flips physics on its head. If you can make gravity just disappear by changing how you're moving, then maybe gravity isn't a force at all, not like a cosmic pull. Instead, Einstein realized what we experience as gravity is actually just us moving through a universe that is warped, that is curved.
Now, I know what you're thinking. Curved space-time sounds, pretty out there and hard to imagine. So let's bring it right back down to Earth with an analogy we can all get. We know the Earth is round, a sphere. So how come all our maps are flat?
Well, it all comes down to scale, doesn't it? If you're planning a road trip across, say, Kansas, a single flat map works just fine. Over that distance, the Earth's curve is so tiny it basically doesn't matter. But now try to plan a trip from Amsterdam all the way to Vladivostok. A single flat map of that whole area, it's going to be stretched and distorted and just plain wrong. The curvature is huge, and you absolutely cannot ignore it.
So what's the solution? How do map makers handle this? Simple. You break the problem down into smaller pieces. You use what we can call a space patch, a small local map that is perfectly flat and accurate for its own little region. A map of your city, for instance, is a perfect little space patch.
So how does this help you on your epic journey? It's actually super simple. You just stitch these flat patches together. You break your long trip into a bunch of short little segments. You use a local, accurate, flat map for each one, and then you just add up the distances. It makes perfect sense, and it works.
Okay, stick with me, because here comes the big leap. This is the genius of it. Einstein realized we could use this exact same logic, not just for the curved space of our planet, but for the curved space-time of our entire universe.
You see where this is going, right? Those local inertial frames we talked about, those little free-falling bubbles where gravity disappears, those are the universe's version of our flat map patches. They are space-time patches, and general relativity is basically the instruction manual for how to stitch all these tiny flat patches together to perfectly describe motion across the vast curved fabric of the cosmos. And this is a huge but. There's one tiny yet world-changing difference between the rule for a space patch and a space-time patch. In space, the rule for distance is basically the Pythagorean theorem. You see that plus sign there. But for space-time, the rule, it has a minus sign between time and space. That one little minus sign changes everything. It's the mathematical guardian of causality. It's what ensures that cause always comes before effect. So this new kind of geometry, this space-time with its weird minus sign, it doesn't just change the math. It totally rewrites the rules of motion. It leads to a new principle. It's going to sound, well, frankly, completely backwards.
So let's ask the question. In this new curved universe, how does a free object, like a planet or a baseball after it leaves the pitcher's hand, how does it know which way to go? If there's no force pulling on it, what's guiding its path?
And the answer, honestly, is one of the most beautiful and mind-bending ideas in all of physics. It's called the principle of maximal aging. What it says is that an object moving freely through the universe will always take the path between 2 points that makes its own personal elapsed time, the time ticking on its own wristwatch, as long as possible. It's like objects are trying to experience the most time they possibly can.
Let's put this side by side, because it's a total shift in thinking. In normal flat space, we learn that the shortest path between 2 points is a straight line. You could call it a principle of minimal length. But in space-time, the natural path, the straight path that a planet or a beam of light follows, is the one with the maximum elapsed time. So get this, objects aren't trying to take the shortest path through space, they're taking the longest path through time. That's what an orbit is. Wild, right?
What this all means is that our most basic, intuitive ideas about the universe, well, they have to go out the window. We're forced to say goodbye to distance and time as these separate, fixed things we can always rely on.
And you know what? Einstein's old professor, Hermann Minkowski, he saw this coming all the way back in 1908. He famously said that space and time by themselves are doomed to become mere shadows. The only thing that's truly real, he said, is their combination, space-time.
Here's the modern, more rock and roll version of that idea. It's a declaration. It means that distance and time, as you and I measure them, aren't fundamental. They're flexible. They're negotiable. The distance you measure between two places, the time you measure on your watch, they are just projections. They're like shadows cast on the wall of a cave by a deeper, four-dimensional reality called space-time. And just like a shadow's length can change depending on where the light is, your measurements of space and time can change depending on your path through space-time.
So let's tie this all together. What's the big takeaway? First, there is no single objective distance or time between two events in the universe. Second, what you measure depends entirely on the path you take to get there. And third, the only thing that's truly real, the only thing everyone in the universe can agree on is the space-time interval, that unbreakable union of the two. But that leaves us with one last massive question, doesn't it? If space and time are just shadows, then what is this deeper, independent reality they are shadows of? What is this thing that their union preserves? Answering that, well, that's the very heart of general relativity.